Hello. And today we're going to take about the second lecture within Chapter 19. We're going to be looking at learning objectives 1 and 2. So we're going to be looking at molar entropies, and we're going to be looking at Gibbs free energy from enthalpy and entropy values. So let's go ahead and get started into molar entropy. Molar entropy is the entropy of 1 mole of a compound at standard conditions, so 1 atmosphere of pressure and 25 degrees Celsius. Down below, I have a table with a couple standard molar entropies. I gave you guys a huge chart with standard molar entropies in there as well. And from that information, you can solve for your delta S naught of a reaction using your products molar entropies minus your reactants molar entropies at standard condition. So if we have some reaction AA plus BB goes to CC plus DD, our delta S of our reaction would equal to C times by the standard mole entropy of C plus D, standard mole entropy of D, and then we subtract out our reactants, A and B. Okay, so let's try it out. We've got the following reaction, N2O4 goes to 2NO2. We want to know what the enthalpy of that reaction, entropy of that reaction would be. So we take our delta S naught of our reaction, set it equal to the S naught of NO2 times by 2 minus the standard entropy of N2O4. So let's try it out. Our S naught of our reaction is equal to 2 moles times by 240.0 joules per mole times by Kelvin minus 1 mole times by 304.3 joules per mole Kelvin. And when we multiply and subtract, we get a value of 175.7 joules per Kelvin. Fantastic. Okay. Let's move on to Gibbs free energy. We can calculate Gibbs free energy at any temperature if the enthalpy and entropy are known. But of course we also use a standard Gibbs free energy as well for this. Delta G naught. That's at 1 atmosphere and 25 degrees Celsius, right? So, just as a note, if we have a delta G of our reaction less than 0, it is spontaneous. Okay, so There's a couple different ways we can get it, but our delta G of our reaction will be equal to our delta H of our reaction minus T times our delta S of our reaction. And if we want to be at standard conditions, delta G naught of reaction equals delta H naught of reaction minus T delta S naught of reaction, where that T is obviously going to be 298 to get to that 25 degrees Celsius. Okay, so let's try and solve for this particular one. So if we have the following reaction, N2 gas plus 3H2 gas goes to 2NH3 gas. Pay attention to your states. We want to solve for our delta H, delta S, and delta G if our delta H of formation is this right here. So first, our delta H of formation, very easy to solve for our delta H of our reaction. We're just going to take that formation value and multiply it by the number of moles we have. So we have our formation 4611 kilojoules per 1 mole, and that's per 1 mole of NH3, right? If we look at our balanced equation that we saw before, we actually have 2 moles of it, so we're going to take that, multiply that by 2 moles of NH3 per reaction, and that gives us a value of 92.22 kilojoules per mole. And our delta S, those values are going to be given in joules, so let's go ahead and convert that into joules per mole. Giving us negative 92220 joules. Oh, just joules. We canceled out the moles. Sorry about that. Okay. So we figured out our delta H of our reaction. Now we want to solve for our delta S of our reaction. Here we're going to do it how we did it before. Take our moles of, or take our product entropies, subtract our reactant entropies, and what we get is 2 moles of our NH3 times by its molar entropy, 192.3 joules per mole Kelvin, minus 1 mole for our N2 times by its molar entropy, 191.5 joules per mole times by Kelvin, plus 2 moles, or sorry, 3 moles of our H2 times by 130.6 joules per mole times by Kelvin. And when we do that, we get a value of negative 198.7 joules per Kelvin. And then we're going to put this into our delta G equation. Delta G naught of our reaction is equal to delta H naught reaction minus T delta S naught reaction. And what we get, put our delta H in there, our temperature of 298. We don't need to specify what temperature because we were talking about standard molar entropies, so we have to be talking about 298. when we solve for this, we get a value of negative 33,000 kilojoules, or 33,000 joules, or 33,000 kilojoules. Negative, so it would be spontaneous. Okay. That is it for this video. Nice short one. We'll continue on with 3 and 4.